Hello, everyone. Welcome back. Today, we're going to be talking about optical rotation. So, essentially, as we go along through the stereochemistry piece, we've already learned most of the important stuff about stereochemistry. But there are a couple things left to talk about, and one of them is this idea of optical rotation. And this idea of optical rotation is essentially just prefaced by the fact that enantiomers, right, you may remember, have the same physical properties. But one thing that they don't share in common is that they actually rotate plane polarized light in different directions, right? And to be exact, it is in equal but opposite directions. Okay? So, what does this actually mean? Well, let's take a look at two enantiomers that will rotate some plane polarized light. And so we're going to take a look at enantiomers of tartaric acid. And so tartaric acid is just this dicarboxylic acid that has a couple of alcohols on dashes or wedges here in the middle. Right, so we have this one here, and then we have likewise its enantiomer, which instead of having the alcohols on the dashes, it will have the alcohols on the wedges, right? And if we wanted to confirm that these were enantiomers, we could, of course, check the stereochemistry of these. You will find that the one here on the left is SS, and the one on the right is RR. So all the stereochemistry is swapped. Therefore, these are enantiomers. So, the interesting thing about these two structures is that the one on the left-hand side rotates plane polarized light to the left, whereas the structure on the right rotates plane polarized light to the right. Okay? So essentially what we're saying is that these two different enantiomers are kind of twisting light in one direction or the other. And notice that one of them is, of course, turning it to the left, and the other one is turning it to the right, and they will do it in equal amount. So, in order to really understand what this idea is of the rotation of plane polarized light, we actually need to understand what plane polarized light is. So, if we're talking about something that is plane polarized, we are essentially saying that the light is coming out as a flat plane, right? Hence the word plane polarized. And it's essentially just saying the light is not scattered, right? Because if you think about a general light bulb, right here will come in my wonderful artistic skills, right? A light bulb is going to emit light, but when it does so, it is in all sorts of directions, right? It's going to be going out in all different cardinal directions. And the thing is, in a 3D space, it will also have that component of course, going in and out of the page. But if you take this and you pass it through what is called a polarizer, just like sunglasses that you may wear, instead of all of this light coming in different directions, the polarizer will force it to only come out in a single direction. And so this right here would be our single plane of polarized light. And as a reminder for geometry, right, a plane is just a flat section of what is essentially a square, right? So it's just like a flat sheet. So you can imagine if this was like a cover, that is what is true of a plane. It's just a flat sheet. Okay? So essentially what we're saying when we're talking about plane polarized is we're saying that it's coming out as a flat sheet of light in one direction. So if we take a look at that tartaric acid that we brought up originally, right, we said that the SS enantiomer, right, where both of these Alcohols are on dashes. We said this rotates light leftwards. Okay, so what does that actually look like? Well, we can imagine that this orange line is our plane of light, right? So it's got to be relatively flat. And so this is our original plane of light. What we're saying this enantiomer does is if it's in solution, it's going to take that original plane and it's going to twist it towards the left. So instead, this red line is going to represent after it is done twisting, right? So it went from the orange line and it twisted over to where that red line is now. And so there's an angle that tells us the difference between the original plane and the amount of rotation, right? So the red, we'll call that rotated light. And then this angle is defined by some axes that go along the normal cardinal directions. So the original plane polarized light, we call this 0 degrees, right? If there's no rotation, then it's not going to leave that 0 degree mark. If it goes towards the right, it's heading towards positive 90 degrees. If it goes towards the left, it's heading towards negative 90 degrees. And then, of course, all the way down here on the bottom, this is going to be our 180 slash negative 180 degrees. So what we're saying essentially is if this enantiomer is in solution, it's going to do this to where it twists plane polarized light in this direction. And the way we actually measure that is by something called polarimetry, right? I would normally have a polarimetry demo to show you all, but this is the best I can do with the situation we're given. So essentially what we're saying is that the light is being twisted towards the negative 90 degree direction, right? And so if light is twisted leftward, right, or rotated leftward, which is towards that negative 90 degrees, um, we call the enantiomer the minus enantiomer, right? Because we're saying that it is twisting it into the minus direction. And the other thing that we say is there's another term for this, which is levorotary, right? And levorotary is essentially saying rotates light left. Okay, and people will usually abbreviate this L. So there's a couple different ways that you can actually name this compound given knowing the enantiomer. Keep in mind this is not useful for IUPAC naming. This is just useful for knowing this terminology if it comes up, right? So this enantiomer that we've been looking at, we can call it the SS enantiomer, which is perfectly fine. But if we're talking about it in terms of how it interacts with light, we can either call it minus tartaric acid, right? Because I said before this is tartaric acid. But we could also call it L tartaric acid, right? Because that minus and L both mean the same thing. It's telling you the direction that it's rotating light. And you may ask yourself, how do we know which direction it rotates, right? And essentially, the only way to know this is by measuring it. All right. So, with that idea being said, we can also take a look at the other enantiomer, right? We can imagine that if we're not looking at this minus, that would mean that the other enantiomer, which is the RR tartaric acid, must be the opposite, right? Because in the case of R, I've already told you, but it rotates light to the right. So if this is our original plane of light, and it rotates the light to the right, it should end up with that red line right there being our rotation, right? And the axes are the same as in our previous example, but notice in this one, the light is being rotated towards the positive 90 degrees. So if it's being rotated towards the positive 90 degrees, that means that it is going towards the plus side, which is why we could also call this plus tartaric acid. And you might think, okay, well, this is also very easy. If the one up there was L, right, this one must be R for meaning towards the right. But sadly, whoever was around when they originally invented this actually made it a little difficult on us. It is actually D tartaric acid, right? Because instead of being like rotating towards the right, the terminology for this is dextro rotary, which means that it rotates right. Again, this was all discovered around Latin times, so a lot of this has to do with Latin terminologies. So essentially what we are saying is when we're looking at enantiomers, they will rotate light one way or the other, right? And essentially these terms, the plus or the D, aka also the minus and the L, they tell you the direction that it is being rotated. Okay? And the thing is with that rotation is that there's a way to quantify it, right? Because every enantiomer is going to rotate light a certain amount. And this rotation is what we call specific rotation. Right? And the idea of specific rotation is it is the specific angle at which a pure enantiomer rotates plane polarized light. Okay? So essentially, this specific angle is going to be um, an intrinsic value, right? Every enantiomer is going to be different for it. And the way that we're actually going to signify this is anytime we're looking at specific rotation, it is going to be shown as a term that looks like this, right? So it's going to be this little thing here where the alpha that is in these brackets. This indicates a rotation value. The 25 indicates the temperature, and then the D, whatever it is down here, this indicates the light source. Okay? With that being said, none of this actually matters for you. All you need to know is how to recognize that it is a specific rotation. Okay, and it will normally be provided to you being said that it is a specific rotation. Now, if we were to take a look at the two molecules we've been looking at this entire time, right, that minus tartaric acid, as well as the plus tartaric acid, what you'd find is that the specific rotation of the minus is negative 12 degrees. The specific rotation of the plus is positive 12 degrees. And so looking at this, it follows the same statement that I made at the beginning of the lecture, that enantiomers rotate plane polarized light in equal but opposite directions, right? Equal magnitude, but opposite signs. That is true for every enantiomer, right? Always true for these enantiomers. And it's just due to the nature of what specific rotation is, right? If you have something that has the exact opposite stereochemistry, it will also rotate light in the exact opposite direction. Okay? So with that being said, we're going to move on to the important part of this lecture, which is actually seeing how mixtures operate with optical rotation, right? So looking at optical rotation of mixtures, because you're not always going to have the pure compound. Now, having the pure compound is great because it should give you a rotation that matches the specific rotation. But there is a good mixture of things in between, right? We have a spectrum that ranges, and we're going to use tartaric acid to actually kind of define what these regions are. So we've already said that on one end of the scale is the first enantiomer that we have talked about, and it is that minus enantiomer. And as a reminder, this rotates light negative 12 degrees. On the other end of the spectrum, we have the plus enantiomer, like we've seen multiple times before, and this rotates light positive 12 degrees. That means there's a range in between these that is going to be meant for mixtures of these two things. Okay? And right in the middle would be something that rotates light 0 degrees. Okay? And this would be a 50% mix of the plus and a 50% mix of the minus. Because essentially what they're going to be doing here in the middle is they cancel each other out, right? Versus on either side with that negative and positive 12, right? Over here on the negative 12 side, this is 100% minus, and on the positive 12 side, this is 100% of the plus, okay? So, even though there's these three regions, there's a lot more in between, right? Because we can say anywhere between this negative 12 and the 0, this is where there is more minus than there is plus, and everywhere between the 0 and positive 12, we are saying there's more plus than minus. Okay? Because essentially, the more of the pure positive stuff you have, the more it's going to lean towards the positive side. The more of the pure negative stuff you have, the more it's going to lean towards that negative side. So there's three different terms that actually relate to the scale up here. The first is a term that we call enantiopure, right? And enantiopure is just one single pure enantiomer, right? So we would say that negative 12 and positive 12 fall under this idea of enantiopure. The second type of term we're going to look at is what is called racemic, right? And keep in mind, these terms are going to be very important as we go throughout the class because racemic is just an equal 50-50 mix of enantiomers. Okay, so essentially that spot in the middle here at 0 degrees is what we would call a racemic mixture. Okay, and racemic is going to be incredibly important because it's going to help us define a lot of things later on as we go through the course. The last term we're going to look at is enantio enriched. This term corresponds to those orange areas between the two, right? Where it's essentially more of one enantiomer but not 100% pure. Okay? And so that's going to correspond to those spaces that we are saying there's more of the plus than the minus, or more of the minus than the plus. Okay? And there is a way for us to actually determine how much of each is in the solution. But the first thing we need to do before we get there is we need to talk about racemic mixtures, right? Because I want to make this very clear before we move on and talk about other important concepts. So if you have a mixture of two enantiomers, right, such as these two tartaric acid enantiomers we've been looking at, and it is a perfect mixture, right? So let's say we have 50% of the plus and 50% of the minus. What we're going to end up seeing is that there's a shorthand way of drawing this. Okay? And that shorthand way of doing so is you can draw a structure, right? So we're going to say this is the same as. You can draw a structure where instead of including that stereochemistry, you draw it out as straight lines, right? So straight lines to each of those alcohols. And what this straight line indicates is that it is a 50-50 mixture. Because remember, we know that these centers are chiral. So they clearly will have stereochemistry. But this straight line indicates that it is a racemic mixture. So from now on, if you see a carbon that should be chiral, right, it should have some stereochemistry attributed to it, but instead it's just a straight line drawn, you can think of it as that straight line right there is 50% of the time a wedge and 50% of the time a dash. Okay? So, that being said, keep that in mind as we go along. Now let's wrap back around to talking about this idea of the scale up here and the rotation of mixtures. So, let's say that we're not given a pure enantiomer of one, we're not given a pure enantiomer of another. How do we figure out how much of each enantiomer is in solution? And to figure this out, right, so this is going to be our section of determining purity of mixtures. So, what we do is we figure something called an observed rotation, right? So, the observed rotation is different from the specific rotation because this is an experimentally measured optical rotation from a mixture. Okay? And the way that we denote this, which is different from the specific rotation, is we have that same little thing indicating it's a rotation. And in the bottom, it just says OBS, and this is just showing it's an observed rotation. Okay, so with that idea in mind, let's take a look at a mixture of tartaric acid. Right, so let's do an example of this. Let's say that someone went into the lab and they measured a mixture that we know contains some tartaric acid. We just don't know how much is in there. So they see that the optical rotation that they observe for this tartaric acid is plus 4 degrees, right? There are literature values for a lot of things that you can look up that'll tell you what their specific rotation is. And tartaric acid is one of those. So if you were to look up the plus specific rotation, right, for tartaric acid, right? So plus tartaric acid has a specific rotation of positive 12 degrees. We could ask ourselves, okay, how much of each enantiomer is in solution? Okay? So how are we going to figure that out? Well, the first thing that we can do is we can actually just take a quick look at some of the values that we've been given. So if the observed value is at plus 4 degrees, what this immediately tells us is that there's more plus tartaric acid than there is minus. Okay? So that tells us that the solution is enantio enriched with the plus enantiomer, right? And we can just gather that from seeing this observed rotation. And so remember, if we're looking up here at this little chart, the reason we know that is because we're between this value of 0 and this value of 12, right? Because we know that the specific rotation of tartaric acid is plus 12. We're setting it plus 4, so we fall somewhere in this orange zone here. Okay? So we know there's more of that, but how do we find out how much more? Well, the first thing we need to do is we need to find something called enantiomeric excess. Okay? And so enantiomeric excess, also known as EE, tells us how much more of one enantiomer there is. So, how do we calculate this? Well, the answer is pretty simple. What you can do is you can actually just take your observed value and divide it by the standard specific rotation, right? Because what this is essentially doing is it's a fraction, right? Your observed rotation over your specific rotation times 100% is going to give us what we call our percent enantiomeric excess or percent EE. So in this case, if we wanted to find our percent EE, it would be plus 4 over plus 12, right? Because our observed rotation was plus 4, our specific rotation is plus 12, times 100% gives us 33.3% EE. So what does this actually mean? Well, it means the same thing that we were talking about when we looked up here. We're saying that in by comparison, we're enantio enriched with the plus enantiomer. This is saying that there is 33.3% more of the plus than the minus. Okay? So if there's 33% more of the plus than the minus, that means that we now just have to figure out how much of the minus there is, right? That would make the most sense. And you can do this through some relatively simple math because we know, given this 33% enantiomeric excess, 100% of the solution minus the EE is going to tell us the percent of mixed enantiomers, right? Because the 33% is saying that is how much extra of one there is. That means the other two are a equal mixture of the rest of the percentage. So that means that in this case, 100 minus the 33.3 is equal to 66% of a racemic mix of plus and minus. Okay? Sorry, it should be 66.6. So essentially, that 66.6% is our racemic mixture portion. So that's saying if we just divide that by 2, we get there's 33.3% of the plus, and that means there's 33.3% of the minus, right? But remember, there is also that 33.3% of the additional plus enantiomer. So in the end, what this is saying for us is that overall, we have 66.6% of the plus enantiomer in solution, and we have 33.3% of the minus enantiomer in solution. And if you want to do a quick check to make sure you are correct, another way to check your enantiomeric excess is essentially the percent of the um, enantiomer that is enriched minus the percent of the enantiomer that has less in solution. What you'll find is the percent EE should match here. So essentially 66.6% minus the 33.3% gives us a percent EE of 33.3%. Okay, so hopefully this makes sense. All you're doing is you are using that observed and specific rotation to get a fraction that is your percent EE, and then you're taking the leftover amount from 100%, you're dividing it by 2, and then you're adding that onto your percent EE to make sure you get the correct mixture of enantiomers. Okay, but that's not the only way that we can actually try and do this. Another way is we could be given the R and the S. That way it's not just a plus or a minus. All right, so let's look at another example. So let's say that you were told that S carvone has a specific rotation of plus 61 degrees. Right? Now keep in mind, R and S do not tell us which direction the light is rotated. The only way we know that is by measuring it. Okay? We are given a mixed sample that has a observed rotation of negative 23 degrees. We could be asked, what is the enantiomeric excess? And then what is the percentage of R and S? Okay, so we have to figure out how to do this. The first thing we're going to do is we're going to take a look at our observed rotation, right? Because it has a negative symbol and our specific rotation has a positive. So what this is telling us is S carvone is the one with the positive rotation. So this is telling us this has more R enantiomer in the mixture. All right. It's always good to identify this at first. It helps you set an idea of what it should be. The other thing that we have to keep in mind is given the specific rotation having a plus 61 degree rotation, that tells us that our carvone, right, has a specific rotation of negative 61 degrees. Okay? Because remember, it's always equal and opposite of the specific rotation of the other one. So let's find our enantiomeric excess. First off, we would say that, okay, if we're doing our observed over our specific, that's negative 23 divided by, and you always want to divide by the same sign, because essentially you just want to make sure you're not making negative percentages. So in this case, it'd be divided by negative 61 times 100% gives us our EE, and we would find that this is 37.7% EE. And I always like to say to remind yourself which one has more of the enantiomer. In this case, it is R, right? Because we already defined that right up there. So we have 37.7% EE of R. All right, well, very simply from here, we just now have to find out how much of the mixture is the equal mix of R and S. And we find that it would be 100 minus our 37.7%, which gives us 62.3% is the mixed R and S, which if we just were to divide that by 2, that tells us it's 31.2% R and it's 31.2% S. Now, as a reminder, that does not tell us the full 100% of the story because now we need to take that EE and add it on here. So that 37.7% enantiomeric excess of R will come into play right now. If we add that onto that 31.2, what we'll find is that the R enantiomer makes up 68.9% of the mixture, and then the S enantiomer makes up that 31.2% of the mixture. Okay? As per usual, practice makes perfect with these, right? So the more you do, the more comfortable you're going to get with it. But with that being said, there are other ways that we can change up these variables to make it a little different, right? Let's take a look at another example. What if this time, instead of being given the specific rotation, we're told something a little different? We are told this time that in a mixture, we see that there is 22% of the R enantiomer, right? It's 22% of the mixture. The S enantiomer is 78% of the mixture. Okay? And then we're told that whenever we went and measured that mixture's optical activity, we found the observed rotation of the mixture is 34 degrees, or negative 34 degrees. And the question becomes, what is the specific rotation of the pure S enantiomer? And we can also ask, what about R? Okay, so let's figure this one out. First thing we need to do is, given this, we kind of have to work backwards. All right, we know the equation to find that specific rotation because we know that the observed divided by the specific times 100% gives us our EE. And there was an equation I used a little earlier that actually allows us to find EE, right? Where the enantiomeric excess is equal to, sorry, the percent EE, should always be percent here, is equal to the percent of the thing that is the more present enantiomer minus the percent of the one that is the less present enantiomer. So in this case, looking at R and S, right, S has more percent of the mix, right? So this is going to be the thing that is the percent enantiomeric excess, right? It is the enantiomer in excess. So that tells us that down here, 78% minus the 22%, right? That is our S minus our R, gives us our percent EE of S, which if you just do the subtraction, you'll find that it is 50% enantiomeric excess of the S enantiomer. So from here, we're given the observed rotation, so we have all of the variables we need to plug in to that equation, right? Because 56% is equal to the observed rotation, which is negative 34, divided by that specific rotation, times 100%. So, doing some math, we can divide both sides by 100, right? And we'll end up with 0.56 equals that negative 34 over the specific rotation. And then if you do some algebra, multiply one side by the specific, both sides by the specific rotation, divide both sides by 0.56, you will end up in a position where your specific rotation equals negative 34 over 0.56, which tells us that the specific rotation for the S enantiomer, right? Because we have to keep in mind we're talking about S because that's the thing that the enantiomeric excess was about, is equal to negative 61 degrees, right? This was rounded, just to make life easier for myself. And that also tells us the second question's answer, right? Because we just figured out what the pure S enantiomer is. What about R? Well, we know that the specific rotations are always equal but opposite. So the specific rotation for the R enantiomer is positive 61 degrees. Okay? So essentially specific rotation, and optical rotation in general is going to be just used for you to figure out what percentage of the mixture is R versus S. Versus also you can figure out the specific rotation of different compounds. All right, so these types of equations are probably what you're going to see on your exam. A lot of this background information is just useful for understanding the concepts behind what is going on, but you won't be asked too much about what plane polarized light is, or drawing some of these pictures. So with that being said, that's everything for this lecture. Next time we'll be talking a little bit about relationships between molecules, and that one's going to be much more heavy on things you're going to see on the exam. See you next time.